Hello, I'd like to welcome you to Lecture 10 of 3N03. We'll start in this lecture our discussion of operational amplifiers. And operational amplifiers are very useful tools in amplifying very weak signals, and they have many interesting applications in electrical engineering and in sensors, even mechanical engineering, civil engineering, any area where you have a sensor. This sensor is usually connected to an operational amplifier circuit that will amplify the voltage in a significant way. I will start this lecture by discussing the ideal op-amp, the practical op-amp, parameters of practical op-amp, and examples. And this will cover sections 12.2 and 12.3 of the textbook. Okay, an operational amplifier is really an amplifier that is capable of supplying very high gain and very high input resistance. The symbol we usually use is this symbol. Okay, so the operational amplifier will have two inputs, a positive input and a negative input, and it will have one output. Okay, and usually it can be connected to two DC supply voltages, say 5 volts and minus 5 volts. In this case, if you connect it to a dual polarity supply voltage, the output can go up to plus 5, say, and go down to negative 5. In some types of op-amps, this one can be grounded, so this is 0, so the output will only be positive, and in that case the output really oscillates between the plus value here, plus 5 or so, and 0. Okay, so it's really an amplifier. It amplifies the difference between the positive terminal voltage and the negative terminal voltage. So if I call this voltage V plus and this one V minus, then V output is equal to a high gain multiplied by V plus minus V minus. This is really effectively the operational amplifier. This is how operational amplifiers look like in reality. Different types of them depending on how they get connected on a PCB and so on. But each one of them really consists of a large number of transistors, hundreds or dozens of transistors inside that will supply this very high input resistance. So very high input resistance means that the current flowing here or here is virtually 0, and very high gain. So the gain can be 10 to the power 5 or 10 to the power 6. So this is how this operational amplifier works. And remember, this block here, even though we use the symbol, but inside this symbol there is a big circuit that contains dozens of transistors, op-amps, and the resistors and so on to supply for you the very high gain required at the output. So this is really what an op-amp is, and it's used very often for weak signals, that's not able to supply enough power, and is used to amplify their voltage level. Very often in this course, I will be asking you to use an assumptions of an ideal op-amp in the same way that we did for diodes. For diodes, we assume that the diode is a switch. When it's closed, it gives you 0 volts. When it's open circuit. Or we assume it's a battery of value 0.7 volts. These are all ideal models. The ideal op-amp model looks something like this. The input resistance seen between the positive and negative terminals is infinite. So this number here is infinity, okay? Even though it does not show, but I can simply here write for you that this one here is equal to infinity. So this number here is equal to infinity. So the impedance seen between these two terminals is open circuit. So this means that there is no current really flowing here, there is no current flowing here. The second assumption is that the gain that you have here, the output, as we agreed, is equal to a very high gain multiplied by the input voltage, and the input voltage is the positive terminal voltage minus the negative terminal voltage. This EV is also an infinite number, so EV here doesn't show, but it's actually infinity. EV will be infinity. The last thing is, when you have this output terminal, usually we have an output resistance. We usually take this output resistance to be 0. So an ideal op-amp will have infinite bandwidth. It can amplify any signal, regardless of its bandwidth, its frequency, whether it's high frequency or low frequency. Of course, it's not the real case. It will have an infinite gain. So this gain here, AV, will be infinite. It have an infinite input resistance. So this infinite meaning that the current flowing here will be 0, the current flowing here will be 0. In reality, there is some current flowing. So, and because of this infinite gain, and in order to create a finite voltage at the output, this circuit will, when you analyze it, you have to assume that the voltage difference between V plus and V minus is virtually 0. Because if you have an infinite value, the only way to get a finite number from multiplying an infinite value by a number is that this number must be 0. So this Vn must be 0 when you multiply it by AV equal to infinity. In that case, you can get a finite number. Okay, so this circuit will really force these two voltages to be equal to one another, especially when you use feedback, and I will show you this later. So just remember these assumptions: very high input resistance, very high gain, 0 output resistance. You don't care about the bandwidth of your signal. The signal can be of any frequency, and this is how we use these assumptions in the ideal model. Okay, let's take a look at one example. This example is not really an ideal op-amp, but it's an op-amp with a very high gain. So here the gain is 10 to the power 6. And this op-amp is connected to a supply voltage 10 volts and minus 10 volts. So it's connected to a dual polarity supply voltage. So the output can be any value between minus 10 and 10. And here you apply some voltage at the input. This is an op-amp itself. And I would like to determine the output from this shown circuit if Vn is equal to 1 volts. So the positive terminal is higher than the negative terminal by 1 volt. The negative terminal here is grounded. Or Vn is equal to minus 1 volt. So the voltage here is less than the voltage here by 1 volt. Would like to see what will be the output of the op-amp. I didn't say anything about an input resistance, then you should assume it is infinity. I didn't say anything about an output resistance, you should assume it's equal to 0. And then you start analyzing your circuit. Of course, the relationship that we have in this case is that V out is equal to the gain multiplied by the difference between the plus and negative voltages. So V naught is equal to A multiplied by V plus minus V minus, but V plus minus V minus is Vn. So V out is equal to 10 to the power 6 Vn. Now, if you multiply this 1 volts by 10 to the power 6, you should be getting 10 to the power 6 volts. But this transistor cannot create any voltage higher than 10 volts. So then the output will saturate at 10 volts. So we say in that case that the output is saturated at 10 volts. Now if Vn is less than 0, it's minus 1 volts. Then Vn is negative. So when you multiply 10 to the power 6 by minus 1 volts, then you get minus 10 to the power 6, minus 10 to the power 6, but this op-amp cannot create a voltage below minus 10 because of the supply voltage. Then the output will be minus 10. So this circuit is really a comparator. It is telling you whether the input is positive or negative. When the input is positive relative to ground, the output will be equal to 10 volts. When the input is negative relative to ground, the output will be equal to minus 10 volts. It's really a comparator circuit. So these are the steps I explained in the previous slide. When Vn is equal to 1 volts, V output is equal to 10 to the power 6, the gain that we have, V plus minus V minus. V plus minus V minus is the input voltage, which in the first case is equal to 1. So this should create a voltage of 10 to the power 6. But remember, this op-amp was connected to a power supply of voltages plus or minus 10. Then the output cannot exceed 10 volts. So the output will saturate at 10 volts. The same thing is happening here when the input is minus 1. V output will be equal to minus 10 to the power 6. So multiply 10 to the power 6 by minus 1. But this means that the output will saturate at minus 10 volts. Now this is useful as a comparator, but it's not useful as an amplifier. I was not able to amplify this signal and make this 1 volt to become 2 volts or 3 volts. I wasn't able to do that. So an op-amp without a feedback circuit is not really that useful. Here it's used as a comparator, but a comparator is really a binary device. It does not offer any amplification. It's either gives you plus VCC or minus VCC. But later I will show you many circuits where the op-amp can be used as an amplifier, but we have to include some sort of feedback. Okay, let's consider one more example, and we'll be talking more about this circuit. This is one of the most useful circuits for op-amps. So this op-amp here, we ground the positive terminal, and then we create a feedback from the output to the negative terminal. This feedback resistor is 2 kilo ohm, and this one here is 1 kilo ohm. And we'd like to determine what will be the output voltage when the input is equal to 1 volts. In this example, we'll have to assume that it's an ideal op-amp. So by assuming ideal op-amp, meaning that the input resistance here is infinity. So this means that there is no current flowing here. The current flowing here is equal to 0. The current flowing here is equal to 0. Okay, so these two currents are 0. One other thing, because the output has to be finite, but this gain here is infinite, then V plus and V minus must be equal. The only way to create a finite output from an infinite gain is that the input voltage will be 0. So when V plus is equal to V minus. So this means that this point here is really what we call a virtual ground. It must be at 0 volts, because this is grounded, this at 0 volts. Then this also must be at 0 volts. Okay, so you can see I assumed an ideal op-amp. I assumed the infinite input resistance, so these two currents will be 0. I assume the infinite gain. If you have an infinite gain, then V plus must be equal to V minus. So this now is virtual ground. This node here is virtual ground. And then I can start to analyze my circuit based on these assumptions. So my target here, if Vin is equal to 1 volts, what will be the value of V out? Okay, let's take a look at this diagram here. If I have a current flowing from the input, this current will have to continue to the output. Why? Because simply there is no current flowing. I minus flowing here is 0. I plus flowing here is 0. So whatever current flows here must continue this way. Also, V minus is grounded, is a virtual ground, because V plus is a virtual ground. So we can simply say that the current I1 is equal to V input minus 0 divided by 1K, and this current must be equal to I2, which is 0 minus V out divided by 2K. This really applying Kirchhoff current law at this point, and taking into account that the voltage here is a virtual ground, 0. So Vn minus 0 over 1K will be equal to 0 minus V out over 2K, or I1 is equal to I2. This is the equation I wrote here. And if you simplify this equation, you multiply by 2K this way, remove the negative sign, you get that the output is equal to minus 2 multiplied by the input. So this is what we call an inverting amplifier. It amplifies the signal at the input, but it gives it a phase shift of minus, of negative sign. So if this was a sign at the input, the output will be minus sign. It's an amplified minus sign. And the amplification ratio here is simply 2. So for V in equal to 1 volts, V out will be equal to minus 2 volts. This is one example why feedback is useful, even though the op-amp itself has an infinite gain. But by using this negative feedback configuration, we were able to create a circuit that creates a gain of minus 2. And we can get a gain of minus 1 or plus 2 or plus 3. There are many configurations we can use the operational amplifier in. But this is one example of how you can limit the gain to a useful value. We can use it in amplifying signals. Practical op-amps, in reality, they do not have an infinite input resistance. The input resistance will be large, say 10 to the power 5, but it's not infinite. They do not have an infinite gain. The gain is pretty large, 10 to the power 4 or 10 to the power 5, but it's not infinity. They don't have a zero output resistance. Usually it is few ohms, but it's not zero. It cannot amplify any signal. Usually it has a finite bandwidth. So there is a bandwidth over which the gain will start to go down. There are so many other simplifications. Of course, if you use an exact model of the op-amp, it complicates circuit analysis significantly. And this is why in many of the examples I'll be asking you to do, I'll ask you to try only the ideal model. But it's good to know the limitations in a practical op-amp model. And the parameters of this op-amp model, this is what you're going to be getting when you open an information sheet for one of the op-amps. So A practical op-amp will consist of a number of stages. We can have an initial stage that will give very high input resistance, a voltage amplification stage that gives very high gain, and then an output stage that gives very low output resistance. Each one of them will consist of many transistors and many resistors and diodes and so on. Very complicated circuits. You can look up the internet. You'll find already the design of these many op-amps. But there are so many parameters that will affect the response of these op-amps. One very important parameter is what we call the common mode rejection ratio of the op-amp. An op-amp is usually used as a differential amplifier. So I would like my V output to be equal to some very high gain multiplied by V plus minus V minus. So try to amplify the difference between the positive terminal voltage and the negative terminal voltage. And the way we can usually use the differential mode, we can ground either the positive terminal or the negative terminal and then apply the signal to the other terminal. This is shown here. So here I grounded the positive terminal while I applied my signal to the negative terminal. Another way of applying the differential voltage is simply to apply the voltage between the positive and the negative terminal, and the output here would be equal to the very high gain multiplied by V plus minus V minus. This gain is called the differential mode gain because this is the gain we are looking for. It amplifies the difference between V plus and V minus. But unfortunately, because the op-amp is not an ideal device, there will also be a component at the output that's proportional to the sum of V plus and V minus. This is called the common mode gain. So in reality, this is not only what you are getting only another signal at the output. It will be way weaker. So this one is way weaker than this one, but it's equal to some common mode gain, which is usually small, multiplied by V plus V minus. So it really sums these two signals. Okay, and the way we can measure that in real applications, that we connect V minus and V plus to the same voltage. In that case, the common mode output, the differential mode output, which depends on the difference, will be 0. And what you measure at the output is simply proportional only to the common mode gain, because V plus is equal to V minus in this case. So these two will be equal to 2V plus or 2V minus. So you can determine what is the common mode gain in that case. So in reality, common mode amplification is a property of practical op-amps, but this common mode gain is usually very small relative to the differential mode gain. This is called open circuit differential mode gain. And if you open the data sheet of any op-amp, you see them talking about the common mode rejection ratio. Common mode rejection ratio, as a ratio, it is the ratio between the differential mode gain and the common mode gain. How much the op-amp amplifies the difference between the two signals, how much the op-amp amplifies the sum of the two signals. Usually this is way higher than this one. This is 10 to the power 5, while this one will be 10, 20, 100, something of that sort. So the ratio between them is a very big ratio, and we can express the common mode also in dBs, sometimes given in dBs. So it's 20 log the differential mode gain divided by the common mode gain. Remember, the differential mode gain is what we are looking for because we want to amplify the difference between the two signals. It's a differential amplifier. While the common mode gain is the thing that we do not want to see. This is when we get an output proportional to their sum, not to their difference. Okay, let's take a look here at one example. The common mode rejection ratio of an op-amp is 76 dB. If the differential gain is 10 to the power 6, find the common mode gain. So here, we're given the common mode rejection ratio as a dB value. We are given the differential mode gain. It's called the AOL, open loop, or A differential. Both of them are fine. And would like to find the other ACM, the common mode gain, which is really the thing that we do not want to see in an ideal op-amp. By definition of the common mode gain in dBs, it's 20 log differential gain over common mode gain. This number is 76 dBs. This number here is 10 to the power 6. So we can divide by 20. 76 over 20 will give us 3.8. Raise both sides to power 10. So you get that A differential over A common mode is equal to 10 to the power 3.8, and this will give you 6309.5. So I can simply say that A common mode is equal to this ratio divided by A differential, which is given. So if you divide this one by this number here, actually it's okay, let's actually if you move this one to the other side, it will be the AD 10 to the power 6 divided by 6309. This is what I have here, okay? And if you divide them, you get 158. So you can see the common mode gain is very small as compared to the differential mode gain. This is 1 million, this is simply 150 or so. So, and ideally this one should be 0 and this one should be infinite. This is what we assume in an ideal op-amp. There are many parameters that you should know about. I'm not going to be asking you any questions about them in midterms or exams or quizzes, but these are properties of a practical op-amp. The first one, I mentioned to you that the op-amp can be connected between a power supply, say 5 volts and minus 5 volts, or 15 volts and minus 15 volts. The output ideally should be able to swing between minus 5 to plus 5 or minus 15 to plus 15. But usually this is not the case. There is some internal drop in the circuit. So V output peak to peak is really the maximum swing that this voltage can go up and down to. So if this is say 15 and minus 15, maybe this amp will be able to go between 14.5 and minus 14.5. It cannot reach the full swing because of internal voltage drop. One other thing I mentioned to you that an ideal op-amp, if you really short the output and the input, so you make the differential voltage 0, say the gain here is 10 to the power 6, in a practical op-amp 10 to the power 6, then the output should be 0. But in reality, even if you make these two equal to 0, the output will not be equal to 0. And you have to apply some tiny differential voltage in order to make this one equal to 0. We call this number the input offset voltage. It can be very tiny number, maybe few millivolts. But ideally, even if they are zeros, you're not going to get a 0 here because of all the complicated circuitry that you have inside the op-amp. One other thing, I mentioned to you that in ideal op-amp, the current I1 and I2 flowing into the positive and negative terminals are 0. In reality, there is some tiny current flowing into I1 and I2. And the sum of these two currents divided by 2, what we call the bias current, the input bias current. Also, we assume that in ideal case, that these two currents are zeros. Well, these two currents will not be 0, they'll be tiny, and there will be some difference between them, and this is what's called the input offset current. So these are all parameters, you find them in the data sheet of any op-amp, of any practical op-amp. The one that we care about more, I would say that the one I may show you some examples how to use them, is the differential input resistance. So if you have the input resistance will not be infinite, but say it's 10 to the power 5. How do we include that in our calculations? So this differential input resistance, the common mode input resistance is when you are having common mode operation, and this one I'm not going to be worrying about it that much because, as I said, our prime use for an op-amp is to amplify the difference between the positive and the negative terminals. The second, one other parameter is the output resistance. Usually you assume it is 0. In reality, it's usually few ohms, so we have to include that sometimes in our calculations. And I'll be showing examples how to do that in a more practical circuits. One other parameter they talk about very often is the slew rate. What if you apply a step input to the op-amp? What is the maximum rate of change that can appear at the output? So the output will take some time to respond. This circuit is called a voltage follower. The output should follow the input, and I'll explain to you that later. So for this circuit, this is called a voltage follower. V out should be equal to Vn. But as you can see, when the input changes from say minus 5 volts to 5 volts, this is a step change. The output will take some time until it reaches this 5 volts, say, at the output. So this is what we call the slew rate, the change that happens in the voltage divided by the time it needed for that change to happen. Of course, an op-amp have a limited frequency response. There is only a bandwidth of frequency in which it can operate. Also, usually you have to take into account the noise introduced in the op-amp circuitry. I'm not going to be picking on these two ones. They are a little bit advanced features, but you should understand that we make an assumption that the bandwidth of the op-amp is sufficient for the signal that we apply.